So before we get into solving the actual question, let's first look at the two main learning goals for this lesson. So the first learning goal is I can draw vector diagrams for given situations, which we're going to do later in this video. And the second one is I know how to calculate a resultant vector and explain what it means with relation to any given problem. And we are also going to be doing that later in this video. So just to expand on the learning goals a bit, let's go over vector diagrams first. Vector diagrams depict the direction and relative magnitude of the sum of multiple vectors. They are in most cases drawn tip to tail. That drawing tip to tail makes it easier to solve the question. And when the tips of the vectors are connected, this is known as the resultant vector. So as you can see here, we have a normal diagram, and using the same vectors, we drew the vector diagram, and as you can see, they are drawn tip to tail, and the blue is the resultant vector connecting the tail of the first vector to the tip of the second vector. So definitely keep this learning goal in mind, because I can assure you we're going to have to use this when solving this problem. So now just to expand on the second learning goal, which is resultant vectors. Resultant vectors are the sum of the vectors when they are put into a vector diagram. In order to calculate them, you must solve the vector diagram using a variety of trigonometric laws and angle patterns, and they represent the vector as a whole, or a single vector. And as you can see in this diagram, v1 plus v2 is equal to r, therefore proving that the resultant vector is the combination of multiple vectors. And to put this into a more real life example, it could be something like looking at the diagram. If v1 was the direction of a boat and v2 was the direction that the waves were going, the resultant would be where the boat would end up, just for some real life context. And also keep this learning goal in mind, because we're going to be using this a lot in the question we're about to solve. And now, the moment we've all been waiting for. The question we've been talking so much about gets revealed. Probably should have edited in a drum roll or something, but it's too late for that now. Anyways, let's get into reading this question and see how we're going to solve it. Two cars get into an accident. Car A is traveling from a bearing of due east with a momentum of 18,000 kilograms meters per second. Car B is traveling from a bearing of north 58 degrees east with a momentum of 15,000 kilograms meters per second. Part A. Draw a vector diagram to represent the situation. Part B. What is the resultant momentum of the two vectors upon impact? Round your answer to the nearest whole number. So let's get into solving these problems using what we just learned from our learning goals. So part A is asking us to draw a vector diagram for the situation given in the question. The best way to do this is to draw the vectors how they are described in the question, and then place them tip to tail in the vector diagram by simply moving one of the vectors. So as you can see here, I'm putting car A, or vector A, on my regular diagram, and then here I'm adding car B, or vector B, and I add the 58 degrees is what it says in the question, so I know they are 32 degrees apart. And then from here, I simply move vector B so that the vectors remain tip to tail, and this gives me my vector diagram. And now that I have the vectors tip to tail, I can find the resultant vector, which is the blue vector I have here on the screen. I can also determine the angle in between vector A and B because they're co-interior angles, so I know I have 90 degrees, and the other part between the y-axis and the green vector is 58 degrees, and 90 plus 58 is 148. So part B is asking me to solve for the resultant momentum of the vectors upon impact. So basically asking me to solve for the magnitude of the resultant vector, and I'm going to do that by applying cosine law. And I use cosine law because I have an isolated angle between two side lengths that I know the values of. So as you can see here, I go on to plug in the magnitude of vector A, which is 18,000, and the magnitude of vector B, which is 15,000. And finally, I plug in the angle on the bottom because it didn't quite fit, but the show must go on, as we say in mathematics. So here I get a value for when I plug these all into my calculator. It's a pretty large value, but I still have to go ahead and root it to get the magnitude of the resultant vector. And here's the moment of truth. Rounding to a whole number, the magnitude of my resultant vector is 31,732 kilograms meters per second. So although we got the magnitude of our resultant vector, the special thing about vectors is they have both direction and magnitude. So using that magnitude, we're going to have to go on and find the direction of this vector. So we're going to do that by applying sine law this time, where we're going to use the magnitude of a resultant vector and its corresponding angle, and we are going to solve for the angle correspondent to B, and that is because that will be the direction of the vector, and I'll explain why in just a second. So here I'm just plugging my values into sine law. I don't show it, but in my calculator I multiply the 15,000, cross multiply it, and then do the inverse of sine to isolate. I get 14.5 as the angle, but because we're rounding to whole numbers, I just round it to 15. So the resultant vector will be 15 degrees from the x-axis no matter where it's placed, and if you remember correctly, the cars collided at the origin originally. So we are going to move the resultant vector back to the origin to get our direction vector. So as you can see here, when we move it, you'll notice that, again, like we said, it's 15 degrees from the x-axis and 75 degrees from the y-axis. So because our directions always come from the y-axis, we can get the direction of south 75 degrees west for this particular vector. So now that we've figured out the magnitude and the direction of the resultant vector, we can formulate our final answer, which is, therefore, the resultant momentum of the cars after they collide will be 32,732 kilograms meters per second at a heading of south 75 degrees west. And here's a vector diagram basically to sum up everything we just did in this question.